At ISRO 942, UTC JWST's NIR spec recorded 3I Atlas carbon monoxide line at 4.7 microns leaping, while the dust continuum stayed stubbornly flat. Normally, when volatile gases surge, dust brightens with them, sublimating ice drags, grains into space building a visible coma. Here, gas rose without the expected haze. Spectral measurements tell us temperature and composition by how atoms and molecules absorb and re-emit light. They should rise together in a comet-like body. This time the rules hesitated. Across the world, telescopes pivoted. NASA and ESA tasking shifted to an around-the-clock relay from Pan-STARRS and the VLT to Hubble and ALMA. A coronagraph blocks the object's glare to pull faint structure from the background. A spectrograph spreads light into its code of lines. The code implied carbon monoxide outgassing, but water's telltale bands remained shy. Then the anomaly deepened. 3I Atlas didn't brighten along a smooth curve like icy visitors usually do. It lingered holding magnitude nearly constant, while its gas features flickered in short pulses. In our models, rotation and solar heating smoothed these changes. Here, the pulses looked timed, as if vents were switching on and off. There is a quiet rumor circulating in the back channels of data analysis teams that the timing of these pulses aligned suspiciously well with terrestrial radar scans, though officially this is dismissed as coincidence. Why would an interstellar object behave like this? Some teams argued for supervolatile pockets, KIO, trapped beneath a dust crust, releasing in bursts. Others doubted the readings entirely, pointing to calibration drift and background sources. Solar physicists were divided on how solar wind pressure could sculpt the jets. Cometary experts invoked sintered ice fractal dust, even a nitrogen-rich crust. Consequences followed. JPL updated trajectory fits, and NASA intensified monitoring with deep space network support. ESA, CNSA, and JAXA added slots on their arrays. Subaru Fast and Meerkat listened and watched. Global collaboration turned curiosity into discipline. Non-gravitational forces appear when jets push on a nucleus, nudging it off a purely Keplerian path. For 3I Atlas, the astrometric residuals hinted at a gentle sunward drift without any matching brightening. Radiation pressure on thin sheets would brighten the object. A hydrogen iceberg would sublimate too fast, a nitrogen shard strains cosmic budgets. The debate is sharp, but shared. This echoes the puzzles of Oumuamua and the clarity of Borisov, yet it is neither. And then something stranger emerged. The CO line narrowed while its centroid crept sunward, suggesting a coherent jet without any corresponding rise in reflected light. The lingering began with a delay no one expected. Instead of racing past the sun in a clean hyperbolic sweep, 3I Atlas slowed in our skies, stretching its close approach window. Normally, interstellar visitors are fleeting, brightening and fading on a predictable curve as they shed gas and dust. But this one hung on its path, hinting at a subtle extra push. Scientists saw the telltale signs of a small, steady thrust like a hand on the rudder, and suddenly, there was time to look closer. NASA responded by tightening the net. Deep Space Network time was shuffled. Parker Solar Probe and Stereo adjusted their monitoring and ESAs. Solar Orbiter slipped in with precision vantage points. A coronagraph works by hiding the sun's blinding disk to reveal the faint whispering structures around it, and now those instruments were whisper hunters. JAXA's Hisaki scanned for ultraviolet signatures. European and Chinese ground arrays tuned in Chile to Hawaii. Amateur observers linked their nights into a continuous watch. You could feel the world lean in. But here is where things take an unexpected turn. The spectral measurements confirmed the object was moving, but the reflectivity remained impossible. The jet was there, the reflectivity wasn't. Some whispered that the absorption lines were too clean, almost artificial, as if the material was engineered to mask its thermal signature. Solar physicists were divided. Some teams argued this pointed to supervolatile pockets, venting through a small nozzle-like crack generating thrust without launching much dust. Others doubted the readings entirely, suspecting instrument drift. And yet independent arrays saw the same signature. Light curves stayed puzzlingly flat. Normally, comets brighten in a predictable rise towards the sun. Here the plateau held. Some suggested a crusted insulating surface with a single active vent. Others pointed to phase angle tricks, geometry masquerading as physics. The implication, a tiny active area doing outsized work. Trajectory fits told their own story. Add a gentle sunward thrust to the model, and the residuals calmed. No exotic sail, required just gas dynamics familiar to comet science, but drawn from a chemistry not quite like home. This echoes the mystery of Oumuamua's push, yet differs in one crucial way. We can see the culprit here. Global context settled into a rhythm. NASA Coordinated Cadence (ESA) kept Solar Orbiter threading the glare. CNSA facilities contributed long baselines, JAXA chased the spectra, and amateurs stitched the night into a continuous film. To understand why this matters, we need to look at diversity. Borisov was a textbook comet. Oumuamua defied the textbook. And 3I Atlas is writing marginal notes in the margins. What hidden mechanism could produce such a transition from silent traveler to lingering, gently thrusting stranger? Moments like this remind us how little we truly understand. But this was only the beginning. 3I Atlas did not fade on schedule. Instead of slipping past the sun and dimming into anonymity, its light curve flattened its motion across the sky, slowed just enough to keep telescopes locked on it longer than predicted. Normally, comets brighten in a predictable curve as ices sublimate and then fade with distance. Hyperbolic interlopers leave quickly. Here, the plateau hinted at a gentle, persistent push, small but real. And here is where things get interesting. The best fit orbit demanded a non-gravitational term, nudging 3I Atlas sideways and stretching the window of observability. There are unverified claims that during this specific window of deceleration, two separate high-frequency feeds from the Deep Space Network went silent for 12 minutes. When they came back online, the telemetry data had been recalibrated. NASA intensified monitoring. Deep Space Network time was rebooked for radar attempts. Hubble schedules were shuffled, and NEOWISE watched in infrared for any warm signature of gas or dust. To understand why this matters, we need to look at the mechanics. If outgassing is uneven, say a few vents opening on one hemisphere, it acts like miniature thrusters. That invisible push can keep an object where Earth-based telescopes can still track it, even as gravity alone says it should have slipped away. Coronagraphs joined the chase. A coronagraph works by blocking the sun's bright disk to reveal faint structures nearby SOHO, and stereo caught fleeting glints of the object against the glare. The images showed no dramatic tail, just a compact coma, tight restrained, almost disciplined. Normally, a vigorous comet would bloom, this one whispered. Spectral measurements tell us what gases are present by their fingerprints in light. ALMA listened for CO, and CN ground-based spectrographs looked for water's telltale bands. The signals were marginal, suggestive, not conclusive. Solar physicists were divided. Some teams argued this pointed to ultra-volatile ices releasing sporadically in micronewts of thrust. Others doubted the readings entirely, seeing instead the clean hand of radiation pressure on a low-density brittle surface. Globally, the campaign widened. ESA's network coordinated twilight observations. JAXA leveraged Subaru's sharp eyes. CNSA analysts compared solar wind models, and amateur astronomers from Chile to Namibia filled nightly gaps. Some argued for a sail, like geometry. Others proposed crusted mantles cracking at dusk and dawn. Yet a few observers noted that the object's adjustments seemed reactive to solar activity rather than passive. Why would an interstellar object behave like this? This echoes the mystery of Oumuamua, yet writes a new margin note lingering as a clue, not a goodbye. NASA escalates the watch as 3I Atlas refuses to fade on schedule its glow, holding steady long after standard models said it should dim. Normally, interstellar visitors brighten near the sun and then slip into the dark on a smooth, predictable curve. This one stalled on a plateau. Teams at JPL extended tracking windows, Hubble grabbed brief snapshots, and NEOWISE probed its heat. The interpretation that rose first, a persistent low throttle vent, was feeding dust into space, keeping the object visible just a little longer. The implication is bigger than a scheduling change activity can be sustained by unfamiliar chemistry, even as an interstellar object departs. A coronagraph view from ESA's solar orbiter then revealed a faint sunward fan, a delicate smudge leaning toward the light. Normally, comet tails point away from the sun, sculpted by radiation and the solar wind. Here, a forward-facing fan hinted at slow lofting, perhaps from a crust that cracks at local sunrise on the rotating body. Scientists read it as proof of gentle directed outgassing. Skeptics countered that the geometry could trick the eye. But there is a theory among those who study propulsion metrics that a forward-facing fan is exactly what you would use to brake against a star's gravity, well, if you wanted to stay a while longer. The light curve added another twist when it declined more slowly than the distance alone would predict. Usually, as an object recedes, brightness falls in a well-behaved way. With 3i Atlas, the fade lagged behind the math. Solar physicists were divided. Some argued for carbon monoxide ices, supervolatiles, that remain active far from the sun. Others suggested radiation pressure was puffing up a cloud of ultralight dust, boosting reflectivity. A few teams doubted the photometry, entirely pointing to calibration, drift near twilight skies. Spectral measurements told a cautious story. Spectroscopy, our way of reading chemical fingerprints in light, hinted at carbon-bearing gases, but little obvious water. Typically, water dominates near solar passes. The absence suggested formation in a colder nursery or a surface sealed by cosmic processing. Astrometry from a global network pan. Stars, the VLT Subaru, and scattered amateur observatories showed a slight sideways nudge in the path, a non-gravitational push. Normally, gravity alone writes the trajectory. Here, a subtle jet altered timing just enough to make 3i Atlas linger in our maps and in our attention. NASA updated Ephemerides' nightly ESO, and JAXA shared rapid reductions. CNSA analysts published independent checks. The deeper implication is elegant motion itself becomes a seismograph of the interior. Field notes turned into coordination. Heliophysics missions like STEREO and Parker Solar Probe tried opportunistic imaging ground-based arrays, stitched nightly mosaics. Classrooms and backyard telescopes joined the cadence from multiple continents. And here is where things take an unexpected turn. The longer we watched, the more the object seemed to answer, and then to pose a harder question. The stitched nightly mosaics revealed an unexpected calm. The Atlas was lingering its glow, holding steady, while its sky track softened. Normally, an interstellar visitor dives past, the sun brightens along a tidy curve, then fades and sprints outward. This one eased its pace and refused to dim on schedule. Teams rechecked ephemerides, recalibrated cameras, and still the plateau remained. It is curious that during this plateau period, several live feeds from major observatories underwent unscheduled maintenance simultaneously. NASA intensified monitoring pivoting Hubble and securing a JWST target of Opportunity as NEOWISE swept through in infrared, and SOHO's coronagraph watched the near-sun backdrop. Spectral measurements tell us which gases are present by their fingerprints of color. The fingerprints for 3i Atlas hinted at carbon-rich volatiles and surprisingly little water vapor. For a sun-warmed traveler, that is not the usual script. Global observatories joined in. ESA's solar orbiter glanced across the dust. JAXA's Hisaki sampled the ultraviolet, and ALMA probed for cold gases, while backyard telescopes kept the cadence. Solar physicists were divided. Some teams argued this pointed to jets firing in a peculiar geometry redistributing momentum like tiny thrusters. Others proposed sunlight was pushing on an unusually fluffy, porous dust cloak, changing its course without much gas at all. A few doubted the readings entirely pointing to faintness at the edge of sensitivity. A brief, delicate tail appeared, then collapsed as the coma's color shifted bluer. Normally, water drives comet activity splitting into OH that radio dishes can hear. Here the OH line was weak, while carbon monoxide and dioxide seemed to do the heavy lifting. This echoes the mystery of Oumuamua, which brightened oddly and accelerated without a clear plume. We haven't seen something like this since that first interstellar surprise. Trajectory fits began to require a small sunward extra force, delaying the predicted departure by days and then by more. Let us break this down. Outgassing acts like a micro-rocket, and radiation pressure is the gentlest breeze imaginable, but across months, both add up. In 3I Atlas, the breeze and the thrusters may have pointed just so, buying it time in our skies. And then the deeper question arrived: what hidden mechanism could produce such a transition? Cometary jets, exotic ices, or a skin of ultralight dust? Some independent researchers have pointed out that the vector of the thrust was mathematically optimal for scanning the inner solar system planets, though this remains in the realm of speculation. The first sign came as a quiet surprise. Y Atlas didn't fade on schedule. Normally, a hyperbolic visitor brightens near the sun, then dims and slips away its light curve, falling in a tidy arc. This one flattened, lingering in brightness, and position a little longer than the math predicted. Scientists read that as a nudge, non-gravitational forces likely outgassing or radiation pressure buying it extra time in our skies. NASA responded by tightening the net. What is usually a measured cadence became a round-the-clock campaign target of opportunity time on Hubble and JWST thermal checks, with NEOWISE and rapid ephemeris updates from JPL navigation teams. To understand why this matters, we need to look at what time gives us more photons, better spectra, and a chance to watch the physics evolve rather than guessing from a single snapshot. Solar observatories added a unique angle. SOHO and Stereo pointed their coronagraphs telescopes that block the sun's glare to reveal faint structures hoping to catch any dust halo. A faint, lopsided veil appeared, not the spherical coma one expects from a typical comet. That asymmetry hinted at jets switching on and off, or a surface shedding dust more like a sail than a spray. The implication was simple and profound: shape and skin mattered as much as ice. Spectral measurements told another story. Normally, comets announce themselves with fingerprints of OHCN and water vapor. Here, teams from Keck, VLT, and Subaru reported meager water lines but stronger hints of carbon-bearing volatiles. Some argued this pointed to exotic ices, CO and CO2, frozen in interstellar winter. Others doubted the readings entirely, noting how sunlight scattered by ultralight dust can mimic gas signals. Solar physicists were divided comet modelers, too. On the ground, amateur astronomers stitched together time series photometry from 3 continents. A subtle beat in the light, the rotation drifted over weeks. Usually spin states are stable here. Torque from jets seemed to be rewriting the object's day length in real time. If so, 3I Atlas was both moving and being moved, a self-modifying traveler. Meanwhile, global partners leaned in. ESA's solar orbiter offered a different vantage. JAXA and CNSA shared calibration frames and tracking refinements, and ALMA listened for faint radio emissions that might betray escaping molecules. This was a planetary-scale effort, a quiet symphony of telescopes turning as one. Historically, this echoed and inverted our lessons from Oumuamua and 2I Borisov. One hid its gases and felt a mysterious push. The other looked like a classic comet. 3I Atlas sat awkwardly between them, a third data point that refused to pick a side. NASA planners watching the clock dusted off rapid intercept studies, the kind that anticipate the ESA Comet interceptor's future role. Not for this object, it was already too late, but for the next one, because a few extra weeks of lingering hinted at what readiness could do. Moments like this remind us how little we truly understand even as our instruments sharpen. The lingering wasn't just a delay. It was an invitation to look closer, to listen longer, and to admit that the void still keeps its best secrets close. What happened next surprised everyone. Atlas lingered in the field of the solar observatories, its glow refusing to fade on schedule. Normally, a comet swings past the sun, brightens fast, then dims along a neat curve as dust disperses and ices shut down. This one hovered in brightness, as if held by an invisible hand, and NASA quietly shifted from watching to watching closely. In that darkened arena, the coma stayed dense, the dust halo persistent, and the outbound tail kept its spine evidence of continued activity when the textbook says it should taper. Ground-based arrays from Hawaii to the Atacama reopened their shutters at every safe solar angle. Normally, comets brighten in a predictable curve tied to distance and sunlight, but the light curve plateaued, suggesting extra, scattering from fine dust or steady jets. Spectral measurements tell us what is boiling off, and here, the fingerprints tilted toward carbon-bearing volatiles, hinting at CO and CO2, hanging on longer than water ice would. Solar physicists were divided. Some teams argued this pointed to exotic ices formed in a colder birthplace between the star's supervolatiles that keep outgassing even as the sun wanes. Others doubted the readings entirely, suggesting instrument scatter near the solar limb or the deceptive geometry of a tail pointing straight at us. ESA's solar orbiter squeezed in off-limb glances. JAXA's Hisaki listened in ultraviolet for faint gas signatures. China's ASOS contributed photometry during tight windows. Amateurs from Namibia to New South Wales stacked thousands of frames to pull a stubborn point from the glare. It felt global and deliberate, a chorus tuning to the same note. Then a subtle asymmetry emerged. A fan-shaped jet rotated and stalled, as if a patch of fresh surface had opened and then crusted over. Normally, jets precess smoothly with rotation, but here they flickered. Dynamics teams at JPL and ESA modeled non-gravitational pushes, and the numbers nudged towards a familiar unsettling cousin, the odd acceleration we saw with Oumuamua, but this time with dust to blame. To understand why this matters, we need to look at momentum. Tiny thrusts from escaping gas can push an object off a pure solar path, and fluffy dust with huge area for its mass sails on sunlight, like a leaf on a breeze. If 3I Atlas carries a skin of ultralight grains, radiation pressure could prolong its visible life, and our assumptions about interstellar debris, dense, inert, simple, begin to soften. Why would an interstellar object behave like this? Perhaps it is less a rock than a relic, a layered archive of ices and foams shaped in a foreign nursery. Some experts suggest that the structural integrity required to maintain such distinct, non-gravitational acceleration without fragmenting implies an internal cohesion that pure ice simply does not possess. As the lingering continued, NASA's tasking deepened target of opportunity. Time queued up radar experiments penciled in if geometry cooperated, and Parker Solar Probe's imagers prepared for one more glance through the sun's bright veil. The void had offered an extra beat, and the world leaned in to listen. NASA intensified the watch. A clean exit was delayed by a lingering glow, so target windows were extended, radar penciled in, and Parker readied one more look through the sun's veil. And here is where things take an unexpected turn. Normally, an interstellar visitor fades on schedule. This one loitered its light curve, flattening as if a gentle hand were on the brake, a hint of subtle forces at play. Coronagraphs and ground arrays converged. A coronagraph masks the sun's disk, so faint surroundings emerge, and there a thread-like tail persisted. Meanwhile, photometry from multiple sites showed a brightness plateau, clues to larger dust or supervolatile ices under crust. Solar physicists were divided. Spectral measurements added intrigue. Spectra split light into fingerprints, and teams worldwide saw steady carbon monoxide and faint cyanogen, while water stayed shy. Some argued for a birthplace far from any star, others warned the glare could mislead. Radar planners leaned in while dynamicists reran the fits. Planetary radar times echoes to bound size, even silence would tighten models. In parallel, a whisper of non-gravitational acceleration emerged less than Oumuamua's puzzle, more than Borisov's steadiness hinting at a middle path. Amateurs stitched the nights between professional snapshots. Multi-continent networks shared light curves, ESA coordinated calibrations, CNSA and JAXA cued assets, and Solar Orbiter, with Parker watched from inside the suns, weather a quiet choreography around a speck from elsewhere. To understand why this matters, we need the pattern. Each visitor redraws the map Rocky Enigma cometary archetype, and now a lingerer that behaves like both. If lingering comes from composition, we have tasted far-off chemistry. If from structure we have met architectures our theories barely allow, if from fragments we are watching a breakup in slow motion. The cameras stayed on the models tightened, and at last, 3i Atlas slipped below reach. Whether the data collected in those final hours was fully released to the public remains a topic of quiet debate in online forums, but officially the file is closed. The extra beat it granted will echo in the quiet readiness for the next messenger. Is it a coincidence that 3 distinct anomalies have entered our system in such a short cosmic time frame, or are we simply finally learning where to look? Time will tell.